and welcome to my project presentation. My name is Nandini and I am an electronics and communication engineering student at Guru Tegh Bahadur Institute of Technology. Today I am very excited to show you my project, an electric vehicle and ADAS dashboard system. In this project, I have combined embedded software, hardware simulation, and a custom user interface. We are using an STM32 Blue Pill microcontroller to do all the main calculations, PICSimLab to simulate our hardware components, and a custom Python script to display our vehicle data in real time. Over the next 20 minutes, I will guide you through how the system is built, how the safety feature works, and finally a live demonstration. Let's look at the basic architecture first. Let's look at how data moves through our system. To make sure the dashboard updates instantly without any lag, the project is divided into three simple parts. First, we have the input layer. In a real electric car, these would be the actual gas and brake pedals, the battery sensors, and proximity sensors. In our simulation, we model them using adjustable slider called potentiometer along with ultrasonic sensor model. Second, we have the processing layer. This is the brain of the vehicle. Driven by the STM32 Blue Pill microcontroller, it reads the sensor voltage, calculates the vehicle physics, and runs the safety rules. Third, we have the visualization layer. The STM32 packages all the vehicle data into a simple line of text and send it wirelessly or via serial cable using QR at a fast speed of 1,15,200 bits per second. A Python script reads this text, decodes it, and instantly updates our screen gogs. To understand how system runs continuously, we can break it down into four simple steps. Step 1, signal acquisition. The microcontroller constantly checks its input pins. It reads value for the accelerator pedal position, the brake pedal position, the battery's state of charge, and the motor temperature. It also tracks the distance data from our ultrasonic sensor. Step 2, processing. Once the STM32 has these raw numbers, it uses simple math formula to turn them into real world values like speed in kilometer per hour, motor torque, and the exact time left before a crash. Step 3, communication bridge. To keep the data organized, the firmware packs all the numbers into a single string. It starts with a dollar sign, separates each value with a comma, and ends with a new line command. It then pushes the string out through the serial port. Step 4 is visualization. The Python dashboard reads this incoming text, separates the number by the commas, and updates the text dashboard screen 10 times every single second. Building an engineering project like this requires step by step planning. Our development roadmap are broken down into four main areas. We started with a setup domain where we configured our coding software STM32 Cube IDE and turned on the microcontroller internal clocks and pins. Next was the dynamic domain. Here we wrote the code to read the analog input and created the math for our vehicle speed and drive profiles. Then we moved to the ADAS domain. We added the code for our ultrasonic sensors to measure distances and built a four-step alarm system to handle dangers. Finally, we completed the telemetry domain where we set up the serial transmission and designed the beautiful graphical dashboard using Python. Let's talk about the vehicle physics. How we read the pedal. The STM32 uses a 12-bit analog to digital converter. This means when you move a slider from minimum to maximum, the microcontroller reads it as a number from 0 to 4095. Our software turns that number into a percentage to understand how hard the driver is pressing the pedal. The script calculates real-time motor torque from 0 to 250 Newton meter and vehicle speed up to 200 km per hour. To make it feel like a real electric car, I programmed three drive modes: Eco mode, Normal mode, Sport mode. Eco mode saves battery by making acceleration gentle. Normal mode gives a smooth standard driving experience. Sport mode gives you instant full power for fast acceleration. We also have regenerative braking. When you let go of the gas and press the brake, the microcontroller calculates the negative torque. This slows the car down and automatically adds a little bit of energy back into our battery percentage. Driver safety is handled by our advanced driver assistance system or ADAS engine. By monitoring the areas around the vehicle, it acts as an extra pair of eyes for the driver. B uses ultrasonic sensor to track the distance of obstacles in the front, left, and right directions. The most important calculation here is the time to collision (TTC). The code automatically divides the distance to an object by how fast the car is moving to see exactly how many seconds are left before a crash. The danger are sorted into four tier alarm system. None, advisory, warning, critical. None. The road is clear and everything is fine. Advisory, an object is noticed far away. Warning, the object is getting closer, lighting up a warning on the display. Critical, the vehicle is about to crash. If the alarm hits critical, a safety state machine completely overrides the driver. It instantly cuts the motor torque to zero and turn on safety lights to stop the car and prevent an accident. Before we move to the live demo, let's take a look at the dashboard interface features. For easy testing, we created a live simulation cell. This lets us type text command directly into a terminal to test things like low battery warning or sudden error without needing to touch the slider. The Python dashboard is designed to look clean and easy to read. It has a circular speedometer that changes color based on how fast you go, a progress bar that changes color as the battery drains, and an embedded line graph that updates live to show our speed history for the last 60 readings. The code uses multi-threading, which means the communication and the screen updates run separately, ensuring the dashboard runs smoothly at 10 frames per second without freezing. Before we jump directly into the software window for our live run, I want to briefly go over the final output results captured during the system execution as shown here on the screen. These two screenshots illustrate exactly how the integrated environment behaves when everything is fully active. You can see the snapshot of PICSimLab simulation interface. It shows all four configuration sliders: our accelerator, brake, state of charge, and temperature inputs actively dialed in. Alongside the three ultrasonic nodes sending distance waveform. You can also spot the virtual terminal window tracking our structured Isaac frame as they leave the microcontroller chip. You can also see the Python telemetry dashboard. The data line from the simulation has been captured, split, and translated into clean visual metrics. The speedometer gauge is registered at 72 km per hour. The battery life progressed bar matches our slider input at 79.7%. And our system state highlight. The vehicle is currently operating smoothly in normal driving modes with zero active safety alarm. This static view proves that our data pipeline behaves perfectly, but to truly appreciate how fast and responsive the system is, we need to see it in action. So let's move away from the presentation deck now and jump straight into our live demonstration part. If you look at the left side of my screen, you can see all our project folders and configuration file organized neatly. Here is my EV dash. Let's open the main code file, which is main.c. This is where the core logic of our electric vehicle runs. If I scroll down here, you can see our ultrasonic and fault code. This part of the firmware constantly checks our distance sensor. If a sensor stops working or detect an immediate danger, the code overrides the system and stops the motor instantly to keep the driver safe. Now that we have reviewed the code file, let's move to the PICSimLab where our hardware simulation run. Now that our code is compiled and ready, we are looking directly at our virtual hardware testing bench inside PICSimLab. Right here in the center of the board is our virtual STM32 Bluepill microcontroller chip. This emulated chip is currently executing the exact binary image of the C code we have just reviewed. Before we start sending input, let me explain how this board layout map to a real electric vehicle architecture. Every slider, sensor, and LED indicator you see on this screen is mapped directly to the internal GPIO pins and peripheral registers of that chip. This workspace allows us to simulate exactly how our compiled firmware interact with physical electronic components in real time. Let's start by looking at the top left section where we have set up our four main analog input channels. These simulate the actual driver control of an electric vehicle connected to pins PA0 through PA3 on our microcontroller. The first slider is accelerator panel on pin PA0. It simulates the variable voltage coming from a physical throttle sensor. The second slider is brake pedal on pin PA1. It handles both mechanical braking force and tells our code when to activate regenerative braking. The third slider is SOC, which is also known as state of charge on pin PA2. It monitors our virtual car's remaining battery capacity. The fourth slider is motor temperature on pin PA3. It represents our motor temperature simulation, allowing us to test how our system react to overheating issue. The STM32 uses its 12-bit analog to digital converter to read the positions of these sliders, translating their analog voltage into digital numbers from 0 to 4095 so our software can compute with vehicle physics. Moving to the right, we have configured three HCSR04 ultrasonic sensor serve as our advanced driver assistance system or ADAS engine. These act as the vehicle radar cones to track nearby hazard. In the center is front sensor. This measures the distance to any vehicle directly ahead of us. To the right of it, it is left sensor. This cover our left side blind spot. On the far right is right sensor. This monitor our right side blind spot. Each sensor block feature an adjustable slider right next to it. By moving these up and down during testing, we can simulate an obstacle coming closer to an to or moving away from our vehicle, allowing the STM32 to calculate the time to collision in real time. If you look just below our main slider, we have a row of hardware status indicator mapped to port B pins. PB8 is our collision indicator. This red LED flashes up if our ADAS detect an imminent collision or severe fault. PB9 and PB10 stands for blind spot detection right and left. They turn on automatically if an object gets too close to our side sensor. We also have our system buzzer connected down on pin PC13 to provide audible warning during critical events. Finally, right here in the sensor, we have our virtual terminal. This block is connected to our serial pin RX on PA9 and TX on PA10. This terminal acts as our hardware debugger. It captured the structure comma separated text frame generated by our code and streamed them out at 1,15,200 bits per second. This complete hardware environment is fully powered up and communicated. Now that we have fully configured our virtual hardware environment inside PICSimLab, it is time to activate our visualization layer using Python. Right now, I have a clean command terminal open on my desktop. To launch our custom graphic application, I need to type some execution command. Python ev.py. Now watch what happened when I hit enter. Here, script fires up instantly, starts a background communication thread, and establishes an active serial connection over our complementary virtual port, COM4. This window that just opened is our live user interface because our communication thread and screen drawing loops are separated using multi-threading. This interface updates smoothly at 10 frames per second without stuttering or locking up. Now we are looking at a live demonstration of a hardware in the loop simulation, focusing on how raw analog data maps directly to a real-time digital interface. On our microcontroller side, we have four primary potentiometer control mapped to pin PA0 through PA3, tracking parameter like accelerator pedal, brake pedal, state of charge, and motor temperature. Right now, our accelerator is sitting at 2.52 volt and state of charge at 1.60. Alongside the telemetry sliders, we have dual ultrasonic distance sensor providing spatial awareness data. These readings feed directly to our ADAS algorithm, communicating via serial transmission over virtual terminal interface via TX-RX pin. Status LED provide quick visual indicator for collision avoidance and blind spot. Now let's see real-time telemetry in action. Watch what happened when I feed different data into the potentiometer. As I vary these analog input on the hardware side, notice how the data transfer instantaneously across our serial communication line. The Python dashboard captured these changes on the fly. the speed update instantly, the calculated accelerator position shift from baseline of 30 baseline of 5%, and the battery metric dynamically recalculate right on the screen. The seamless mapping between our hardware input and Python UI is exactly what makes testing these safely critical ADAS systems so powerful. This project concludes my internship here at Emertxe Technology. A huge thank you to the entire team for this incredible mentorship and hand-on experience during my time here. Thank you for watching.